Both error detection as well as error correction employ the following framework. Basically, you add some redundant information to a frame to detect or correct errors. Typically, what happens is at the sender, you add k bits of redundant data to m bit message. This k is derived from this message through some algorithm. We will cover some algorithms shortly. At the receiver, you reapply the same algorithm on the m message bits to recalculate k and do a comparison to figure out whether the frame is in error or not, and then take a corrective action. So in detection, for example, which Ethernet does, this k is much smaller than m. So for example, Ethernet uses 32 bits for a message of duration roughly 12,000 bits. On the other hand, this error correction codes, they have what is called a code rate, where m is the amount of useful data and this is the total data. So this says what is the portion of the received data that is useful. So for example, in Wi-Fi, these code rates vary from half to 5/6. When it is half, that means you are adding one redundant bit for every bit. And if it is 5/6, that means you are adding one redundant bit for 5 bits. So as you can see, for error correction, the amount of redundancy you add is significantly higher than that of detection. So an important question here is, how are these algorithms that detect and correct errors work? So before we get into the details, here is some theory. Hamming distance is an important concept that captures the error correction and detection capabilities of a code. So in this context, m message bits, when you add k redundant bits to it, this combination is called a code word, and here I have set it to equal to n bits, where n is equal to m plus k. Now Hamming distance is nothing but the number of bits two code words differ in. You can obtain it by XORing the two code words. So for example, if these are the two code words, what do you think the Hamming distance is? That's right, 5. An algorithm translates the m message bits to an n-bit code word. Now there are 2 to the power of n possible code words. Out of these 2 to the power of n code words, how many are legal code words? By legal, I mean actually get transmitted. This is only 2 to the power of m because you have m message bits. That means you have total of 2 to the power of m messages, and each of these messages gets translated into a code word, distinct code word. Thereby you only have 2 to the power of m legal code words. An algorithm basically translates these messages into code words, and this is called a code. That is, the legal code words form a code. Now Hamming distance of a code is given here, where among the list of legal code words, take all combinations of two code words, find the Hamming distance, and the minimum over all of these is the Hamming distance of the code. So what this basically means is that any two code words that are part of this code differ by a distance of at least d. That is what it means. So the error detection and correction capabilities are a function of the code's Hamming distance. Let me reiterate this once more. So when a code has a Hamming distance of d, that means that any two code words that are part of this code will differ by a distance of at least d. So given this, how many errors do you think you can detect for a code whose Hamming distance is d? I want this as a function of d. This is not that difficult to solve. Think carefully. So the answer is d minus 1. Basically, you won't be able to detect an error if one code word got converted into another code word, and for this to happen, you need at least d bit changes. So as long as the errors are under d, you should be able to detect an error. So given this, can you guess how many errors a code word with distance d can correct? So the answer is d minus 1 by 2, because with these many number of errors, the received code word that is in error is still closer to the original code word than any other code word. Thereby you will be able to correct. Here is an example to illustrate these things. So here is a repetition code where when you want to transmit the bit 0, you transmit 0, 0, 0, and when you want to transmit the bit 1, you transmit 1, 1, 1. So this repetition code reminds me of a Supandi joke in Tinkle. I don't know how many of you follow this book, but anyways, Supandi is a very innocent person who creates very funny situations. So here is the joke. So one day he is going in the bus and he asks for 2 tickets from the ticket conductor. This ticket conductor sees that he is traveling alone and he says, "Why do you want 2 tickets? So Supandi tells him that if I lose 1 ticket, I will have another ticket. So this bus conductor thinks this guy is crazy, but anyway, for argument's sake, he asks, "What if you lose both tickets?" So Supandi says, "I have a bus pass." So that's repetition code in action. Thereby, in this case, we have m is 1 because it's only 1 bit, k is 2, so we are adding 2 redundant bits, and n is 3. So given that n is 3, there are 8, so n is 3, so there are 8 possible code words, of which how many are legal? Only 2. There are only 2 legal code words. Now given this, what is the Hamming distance of the code? So the Hamming distance is 3 because these 2 legal code words, if you do an XOR between them, that is going to turn out to be 3. You also notice that the code rate is 1/3, that is only 1/3 of the data stream has useful content. The others are all redundant. So given this, how many errors can this code detect and how many errors can it correct? So if you plug in the formula of d minus 1, this is going to detect 2 errors. And if you plug in the formula of d minus 1 over 2, you will see that it can correct up to 1 error. So what's happening here is that any of these received bits, so rather received code words, are going to be decoded as the bit 0, and any of these received code words are going to be decoded as the bit 1. Now if 0 were transmitted, in which case it is 0, 0, 0, if you make 1 error where let's say this translated into 0, 1, 0, this is still closer to this code because the Hamming distance is only 1. But if you made 2 errors, this may translate into 0, 1, 1. Now this is closer to 1, 1, 1. Thereby this will decode as 1. That is why you cannot correct 2 errors, but you can still detect it because you know that these are the only 2 valid code words and this does not correspond to either of them. Thereby you are able to detect this, but you cannot correct this because this is now closer to 1. This code as such is a very simple code and is not particularly useful. Its correction as well as detection capabilities are very poor, so you don't want such codes. So when you're designing codes, these are some of the considerations. You want to keep k to the smallest possible so that you can achieve high code rates. You want to keep the redundancy low. But at the same time, you want to maximize the Hamming distance so that your error correction and detection capabilities are high. At the same time, you don't want to design codes that are very complex because it's not easy to implement them. In other words, you want easy encoding and decoding, which will require minimal memory and processing time. So a lot of the research goes in achieving these goals. So as part of this course, we will focus on error detection algorithms. Some of these codes I'm going to cover shortly. And we will also focus on error recovery through retransmissions in the form of reliable transfer. We are not going to focus on error correction. There are many such codes, Reed-Solomon convolution codes, turbo codes, because these are typically used in wireless, which is again not the focus of this course. So here is a quick summary. So we saw that it is important to detect errors both for data fidelity as well as not wasting resources. Once you detect errors, you can recover from them either through forward error correction or through retransmission, and there are some inherent trade-offs here. So you need to do either FEC or retransmission based on the particular situation. We also looked at a framework for error detection and capability. Basically, we covered Hamming distance and what the capabilities of a code are in terms of error detection and correction. And we also looked at the design consideration for the algorithm that does error detection and correction. So going forward, we will cover error detection in detail.